Um, so first off, welcome everyone. It is actually a really beautiful day here in Austin, Texas. So thanks for joining us. Thank you for putting in some of your effort this afternoon and giving our presentations your attention. Welcome. I am Charlie Day. I am the Director of Training and Professional Development at the Texas Advanced Computing Center, as well as the DesignSafe Training Lead. So if you haven't had a chance yet, please hit the DesignSafe page. We have some really cool news stories out there, and I believe the Dataset Awards have been, I'm not sure if they've been announced yet, but they're going to be announced soon, so keep an eye out on our DesignSafe main page. So before we get started though from our presenters, I just want to tell you all that we really need your feedback and we appreciate your feedback. So if you have your phones available, if you can scan that QR code and take our survey, that way we can get a better understanding of what kind of events you're looking for, what kind of events you'd like to attend in the future, and any feedback you'd like to give the DesignSafe team on your experiences using DesignSafe and coming to our webinars. We would really appreciate that. That lets us build better webinars for you all. All right, so with that, let me introduce our presenters today. Our presenters are Jamie Paget, who actually is one of my favorite people on DesignSafe. She's a professor at the Department of Civil and Environmental Engineering at Rice University in Houston, Texas. Her research focuses on the application of probabilistic models for risk assessment of infrastructure and emphasizes a structural portfolio such as regional portfolios of bridges and oil storage tanks exposed to multiple hazards, including earthquakes, hurricanes, aging deterioration. She's very well known in her industry. She's published over 200 articles and is a PI on the DesignSafe project. Also with her today is Catalina Gonzalez Duenas. Pardon me if I mispronounced that. Who is a PhD candidate working under the supervision of Dr. Paget. And she has her MS and BS degree in civil engineering from Columbia, and their emphasis is on structural engineering. So we're very much looking forward to their talk. They will be talking today about leveraging DesignSafe for disaster debris modeling and a workflow for coupled human-built natural systems. So there's a complex interaction of natural hazards such as hurricanes with the dynamics of coastal areas lead to important challenges in the estimation of disaster impacts on consequences in these regions. So they will be talking about the science behind their study, and then they'll be talking about the workflow and give you a hands-on section after their presentation. So with that, I'm going to be handing it off to Catalina and Jamie. Thank you so much for being with us this afternoon. We really appreciate your time on this, and we really appreciate your efforts on DesignSafe. So thank you.
Thank you so much, Charlie. I think we will go ahead and try to share screen as well to launch the presentation. And let me say a big thank you to Charlie and Scott, and then to all of you who are here today. I see some old friends and faces and some new ones as well. So I'm really excited that at least we have these virtual venues to continue to connect these days. And I'm happy to share with you a bit about an ongoing project that we have. It's a collaborative project between Rice University and Texas A&M Galveston. And I'll give you a bit of kind of an update on the overview of that project. But we thought this might be a good opportunity to share with you some preliminary results from this project. It's an NSF project that was recently funded, but emphasize how we are leveraging DesignSafe kind of from the start to finish on this project. We were able to leverage DesignSafe in the early proposal development phases and our early work in this project to just show how the tools from the cyber infrastructure are enabling these types of studies, which are multidisciplinary, collaborative, distributed teams. So we'll be looking in the space of disaster debris modeling, and Catalina will be really taking on the bulk of the presentation today. This constitutes a portion of her PhD work, which is in kind of that broader coastal performance-based engineering space. And so she'll really be showing you the meat of the talk today and walking through the hands-on demo and DesignSafe with you. We'll move to the next slide, please. So this image perhaps hits you in the gut like it hits me. It's a reminder of things that actually happen somewhat in our backyard. I'm here at Rice University in Houston. These are images from Hurricane Ike, but you've seen similar images of coastal hurricane hazards and some of their cascading consequences for decades now, and unfortunately quite a few just in the last say 5 years. This image should remind you of the potential exposure of coastal development, the vulnerability of our built environment, and of course that interplay with human systems in terms of the types of development, the siting, the shifting of populations in these coastal zones. And what we certainly see here in prevalence is debris from this coastal multi-hazard storm event. And I emphasize the multi-hazard piece because we know that a hurricane event brings with it wind, surge, wave, all that contribute to potential damage to the built environment and cascading consequences like debris, which is the focus of this particular study. Next slide, please. So the figure here gives you a bit of an overarching view into our project, which is looking at this complex coupling between human-built and natural systems. So we use debris as essentially this lens of viewing these coupled systems problems. And I think debris is actually a very classic case of this because we have natural systems in terms of not only the natural hazards and the loads that they produce, but also debris brings with it examples of woody or vegetative debris, along with those that are generated from loads on our built systems and our built infrastructure. So in terms of our built environment and human systems, we're looking at not only socio-demographic composition of human systems along the coast, potential projections into the future, and how in particular land use and land cover may change over time to influence this intersection between systems that may produce debris. So the project has a bit of a long-ranging view at looking at probabilistic modeling of debris generation, keeping in mind the different sources of debris and interactions between these various systems that generate debris. There's also coupling on sort of the back end beyond just the debris generation piece, but what are some of the consequences of debris within our coastal communities? Looking, for example, at cascading consequences like the potential inequitable distribution of debris amongst coastal residents, as well as inhibition of things like access to critical facilities or impairing transportation networks because we have debris and in some cases timely processes for debris removal that can affect mobility within coastal communities. So that gives you a bit of a sense of some of the motivation behind the project and the long-ranging goals of this study. I also want to acknowledge our collaborators. You'll meet Catalina and myself today, but Wes Highfield is our co-PI from Texas A&M at Galveston, and Mitchell Meads is another PhD student who's working on this project from Texas A&M. Next slide. So what Catalina will be walking you through today is kind of one of the first phases of this project, which has been looking at predictive modeling of disaster debris, particularly in this coastal space, where we have not only wind-borne debris, but also that that's generated from surge and wave action in these coastal spaces. And the first focus has been on developing physics-guided or physics-informed machine learning models. So data-driven models whose predictors are inspired by our potential knowledge of the physics behind debris motion or the vulnerability of the built environment. And in some cases, learning from this process, learning which of these predictors may be most critical and looking at predicting things like debris presence or debris volume, which could influence mobility as an example after an event. So Catalina will be walking you through some of the framework that we've developed for this type of modeling. And of course, we're happy to chat later about some of the other kind of longer ranging goals of the project if we have time. So with that, I'll pass it to Catalina, and thank you all again for joining us today.
Thank you, Dr. Payet, and I hope everyone is well. So as Dr. Payet mentioned, we're going to walk the first part of this project where we consider certain predictors of the storm generation and land cover of the region. So first, I'm going to talk a little bit about more the motivation and some of the research gaps that we're trying to address in this project, follow what an objective, the computational framework that we have proposed to address these problems. I'm going to walk you through how we're going to do this, some of the preliminary results of the debris volume predictive model, and some conclusions on the ongoing work that we have right now. And then the second part of the talk, as it was mentioned at the beginning, we're going to do some hands-on exercise in DesignSafe. So very excited about this. So as Dr. Payet was mentioning, debris by itself is a big problem. The debris removal costs are big. It was estimated that after Hurricane Ike, the debris removal activities were around $200 to $3 million. After Hurricane Ike, it was estimated in $752 million. And this debris can also accumulate in roads, in bridges, can jeopardize the accessibility of vulnerable communities to critical services, such as hospitals. And the other part is that the improper disposal of this debris, and it's immediately spreading because there are some debris that can turn toxic when it comes in contact with water, such as plywood, can affect the community in aspects such as public health. For example, here we have a small video of Fredwood, Texas, in the aftermath of Hurricane Ike, just a few days after the storm, where we can see the real impact of the storm in the daily life of the community, and even like the part of being in roads in this side. So the issues that existing debris estimation models are usually focused on wind-induced debris and produce a big error, such as like nearly 50% in their estimates. There is limited knowledge on the drivers of debris. There is also constant changes in the coastal landscapes, the developing patterns that can influence the debris composition over a region. And we know that climate change and sea level rise might exacerbate this risk in the future. So we know that for estimated such a complex process, such as the waterborne debris, we need to evaluate the interactions of the built environment, the natural environment, other infrastructure systems, and even like the community, what are the socio-demographics of it. But the issue is that how do we model these interactions when we don't have a physics-based model yet that can help us to predict what is going to be the debris spreading and the debris generation in the aftermath of a storm or hurricane event. So for this, we can leverage the potential of data. So what we're going to, some of the objectives of the general project is to derive probabilistic models of debris that are going to be physics informed in the sense of these predictors that Dr. Payet mentioned, to derive some data-driven models for predicting the volume of waterborne debris in the aftermath of a storm. We want to model these couple effects of human developing patterns, if we can do some policies in the urban planning and how these affect storm-induced debris. We also want to examine some of the cascading consequences of debris. For example, if it's going to impact some of the transportation networks, and how can that jeopardize accessibility, or even like aspects related to the social vulnerability of the community. And some of the other objectives of the project are to disseminate these lessons via some, for example, this webinar, developing learning modules on DesignSafe Infrastructure. So just the scope of this talk, we're going to walk you through a preliminary model where we develop a probabilistic framework to estimate the amount of waterborne debris, and we're leveraging the potential of this data. Specifically, we have the debris removal database in the aftermath of Hurricane Ike, which hit the Houston and Galveston region in 2008. Something important to mention here is that Hurricane Ike was predominantly a surge and wave hurricane event. So it's the perfect case study to analyze the impact of waterborne debris on a region. So first, we're going to talk a little bit about the computational framework and how we're using this data, combining with the predictors to derive a model of debris volume. So first, we start with data, with the data related to the predictors. In this case, we're going to talk about land cover and storm intensity parameters that I'm just going to talk about in the next slides. We're going to use these to develop a debris presence model that is actually going to inform a debris volume model. Why? The debris presence model can actually tell us information related of regions that, for example, for some topographical features or some man-made fences, for example, can tend to accumulate debris. So we're exploring how doing this dual layer model, how coupling these two models, debris presence and debris volume, can give us a better prediction of debris. So in the data side, we're going to leverage some predictors related with the multi-hazard aspects of the storm and the land cover composition of Galveston Island. And in the response, we have two different databases, the debris volume that we gather after, that we obtain in the aftermath of Hurricane Ike, and the debris presence that was actually extracted from satellite imagery in the aftermath of Hurricane Ike. So regions that where debris was observed were like labeled with 1 or 0, depending on the debris presence in the area. So in this preliminary model, we're using storm predictors and loss cover predictors due to their influence in the debris generation and spreading process. So for example, if we think in the aftermath of like when the hurricane event is in a region, the loads that are going to be imposed, for example, in structures or the natural environment such as tree, is going to dictate, for example, if these structures or trees are going to fail, and that is going to become a potential source of debris in the aftermath of the hurricane. And also when we're thinking, for example, about the land cover predictors, it will tell us the composition of the debris. So if we have areas that are predominantly construction or areas that are open lands or have a lot of trees. And we want to understand what might be the influence of these two like set of parameters in the debris generation process. So we start with a database that has more than 200,000 locations in the Houston-Galveston region. And this database has information related to the debris class. So if it is, for example, construction debris, vegetation debris, or mixed debris, that is actually a mix of both. It has the debris quantity, that is actually our key response variable. So it has the debris volume that was collected for particular locations. We have the disposal site where it was. And how do we know where the location is? That it was collected it was connected manually. So we have the address. The issue with this is that since it was collected by a lot of people, there are a lot of addresses that are duplicated, there are a lot of addresses that are not complete, and there are a lot of typos. So our objective to actually do the geospatial analysis was not only to get the address, but the geographical location. So we needed the longitude and the latitude of each one of these places. So leveraging the DesignSafe Infrastructure, Google APIs, and Python scripts, we developed some scripts that could take these addresses and geocode it. So what we will have, for example, this is some screenshot of the actual database. We will have the address that in our case is the input string. And what we do with these codes is assign to each one of those places the geographical coordinates. So how do we start with the methodology? The first thing we do is defining the region of interest. So since here we're studying the waterborne debris, we define the area by the area that is covered actually with water, that is with surge, since this debris is transported by water. We divide this area into different grids. to analyze what is going to be the debris accumulation in one of these sub-regions. In this case, we're using a 500-meter grid cell size. Then, for example, using the satellite imagery, we identified regions in this area where debris was seen. So we just use the satellite imagery, and in this case, for example, if it was debris there, we assign a label of 1, and if there is no debris, we assign a label of 0. And we leverage the geocoded debris volume database to get the response variable for the debris volume. For each one of those areas, we also extract the parameters of interest. For example, here we have the search, so we have some things related with the intensity parameters of the storm and some other related with the land cover parameters of the region. And then we use this information to first formulate a classification model for the debris presence. And with this, we also leverage this model and the data of the storm to propose a regression model for the debris volume. So how do we leverage the DesignSafe civil infrastructure to help us in this process? So the first thing is the data depot. So since this is a collaborative project, the data depot is always very handy because it can help in the data management part. So we have a project, we can share the data between the two groups, even the preliminary data, the data that is like related to the final models. More importantly is, since we have the data there, first, we have a copy. It's always going to be on the cloud. And so you don't have the possibility of losing it. That is always very scary for a graduate student. And more importantly, is you will have access to the data in the analysis tools within DesignSafe. So for example, in some of the tools and applications that we're leveraging in this study, on the simulation side, we have AdSeer, that is also that is actually a software that can let us know what is the intensity measures of the storms, of the surge height, wave height, wind speed. So it helps us with the hazard analysis of the study. In the visualization and also for the part of geospatial analysis, we have QGIS, that is the one that we're going to leverage today. So one important thing that we have to see in these studies, even when we're doing machine learning models or when we're doing risk-related studies over a region, what we need to do is to couple different data between the storm, the infrastructure system that we're analyzing. So GIS softwares always help us in this part. And the analysis, for example, we have Jupyter notebooks and Python scripts that not only help us in the data analysis part on developing the machine learning model itself, but it also helps us in data pre-processing and post-processing. So for example, we will have a data processing related to the data management, that it was something that we discussed previously, related to the geocoding of the database. Related with the hazard analysis, we will have some files that are going to be the output of AdSeer, but enable to us to use it in a GIS software analysis, such as QGIS, we need to read those files and get it into a format that is useful for us. So we're going to see that a little bit on the Handson exercise. It also helps us in the geospatial analysis. So if we are, for example, analyzing not just one storm, but an ensemble of storms, this process can be time-consuming and repetitive. So we can automate this data processing part. It can also help us in the visualization, not only of the different infrastructure systems that we're analyzing, but also of the hazard analysis and how it varies over a region. And the geospatial analysis, as I mentioned previously, will help us to couple the different resolutions of the data related with the hazard on the part of, for example, the vulnerability of the built environment. So coming back to the model, we have in total for this case, in this grid cell size, we have 1973 observations. For those one, and to test the performance of the computational framework that we are developing, we set aside 300 observations. And of the remaining 1673 observations, we divide 70% for the training of the machine learning models and to perform hyperparameter tuning. 30% of this data set is going to be for the test set to select the model that is going to have the best performance for both tasks, predicting debris presence and debris volume. And as I mentioned, the blind test set it's a data that is set aside from the beginning to actually test the performance of the proposed framework. So here are some preliminary results of the model. We have here on the left, we have the debris presence model, and on the right, the debris volume model. We tested different methods, machine learning algorithms, and we saw that actually ensemble learning performed the best for both tasks. It had the least misclassification error for debris presence, and I had the least normalized root mean square error for the debris volume model. So now we propose a scheme to compare how is this dual layer model behaving. So we use this blind test data set. And the first thing we do is, okay, let's see, we use this test set to predict the debris presence. And then we leverage this to actually inform the debris volume as one of the predictors, also related, apart from the ones related with the storm and the land cover. And we used to give us a prediction of debris volume over the region. Another way of doing this is having the debris volume model by its own without informing anything regarding the debris presence and make a prediction of the debris volume. And the third path could be using the actual debris presence data that we will get from satellite imagery, for example, to inform the debris volume model to make the prediction of debris volume. So we tested the different paths of kind of predicting debris volume, and we see that actually the models that incorporate debris presence as one of the predictors perform better than the one that doesn't incorporate debris presence data. And the difference in the performance between the dual layer model, the one that we trained with the debris volume, it's very similar to the debris volume prediction that actually uses the debris presence data, which tells us that the debris presence model behaved very well. And we wouldn't even be able to go again through the whole process of labeling the satellite imagery, and we would be able to use this surrogate model to inform a debris volume model. So how would you be able to apply this model? For example, here we have a prediction of debris in Galveston Island that is informed by the 2020 land cover parameters of the region, and also storm intensity parameters coming from Storm FEMA 36. That is a probabilistic storm that will give you still approximately still water elevations of a 500-year return storm in the Houston Galveston region. So it will help in community planning, resilient planning related to activities with debris removal. So some conclusions of this preliminary work, we propose a framework to estimate the volume of waterborne debris, leveraging the potential of data. We saw the viability of using machine learning techniques to actually help us understand a little bit about this complex model phenomena, such as waterborne debris. There is a ton of data that exists that actually may be leveraged for these data-driven models. Here we just use the data coming from one storm that it was actually Hurricane Ike, but the performance of the models is also going to be better if we incorporate data, for example, from other storms and in different regions. We saw how the DesignSafe Infrastructure help us in the workflow of analysis of the data processing and the visualization tasks. And in general, these models are going to be useful tools to inform decision-making, facilitate recovery efforts in the aftermath of storms, and improve resource allocation following storm events. So a little bit about the work that we're doing right now is, as I mentioned in this preliminary model, we just leverage two sets of predictors related with the storm and related with the land cover, but there are multiple aspects that are going to have an influence in the regeneration and spreading process related with the built environment, the demographics, and the natural environment of the region. So what we're doing right now, sorry about that. So what we're doing right now in the model is expanding the set of parameters. For example, we will have different things that will say the density of trees in a particular region. With the built environment, we have things related to the vulnerability of the built environment. And we're going to inform machine learning models to actually have a field of debris volume over a region. So for example, one of the new predictors that we're testing is related with the fragility of a structure. So for example, if we analyze a single cell, we will have different buildings in that cell. And what we can do is see in each cell where is the potential of construction debris that can be generated in the aftermath of the storm. We propose a new predictor related with this potential of construction debris, where we, for each one of the buildings in a grade cell, we evaluate the probability of failure. In this case, we're using the fragility model proposed by Dr. Tomicek in the aftermath of Hurricane Ike. We evaluate the probability of failure of each one of these buildings failing. We weight this by the area of each one of these buildings, and we repeat that for each one of the buildings in a grade cell. So we tested this parameter and some other parameters related with the built environment, where we see that actually combining it with a Gaussian process, that is a different machine learning technique that can give us probabilistic estimates of debris over a region, not just like, let's say, the mean value. And we're seeing that the models are performing well, actually kind of hinting in the importance of bringing this domain expertise into selecting different sets of predictors for this type of complex phenomena. So as I mentioned, Gaussian processes not only like help us in the part of giving us probabilistic estimates, but actually also help us in taking into account maybe some spatial correlations between regions that have a lot of debris. So it will give us, for example, the mean value, but it will also give us things related to the lower and upper bound confidence intervals for the prediction. Some other part of our ongoing work is related to how climate change and changes in socio-demographic characteristics of the region can influence hurricane-induced debris. So what we're doing is coupling population projections related to different scenarios of climate change, using these to inform some projected land cover that will also change what is the storm output, and informing these storms also by different parameters such as sea level rise. And what we want to ultimately do is see how this hurricane-induced debris and the storm, actually the impact of the storm, can affect the community, not only on present conditions, but in the future. So here I'm going to make a stop to hear some questions related to this part of the talk, and then we're going to move to the next part. So if there are any questions, we can respond that now.
I see Jamie's been answering some questions in the chat, which is great.
Oh,
thanks, Jamie.
Okay.
You probably didn't know, Catalina, because you were sharing your screen and you can't see anything on Zoom.
Yeah, it was coming up, but I didn't want to see it because I was going to.
So if anyone has a question, feel free to type it in, or you can unmute and ask Jamie and Catalina if you'd like.
Yeah, and thanks for the great questions in the chat. I think just as a quick follow on to those, I don't think I gave you a direct response, Jasmine, on the timeline. I do think it may be a year or more in the making before that final debris data set is published, just to be upfront with you, because we're merging it with all of these other new predictors and new types of data sets that can maybe inform a better predictive model. But our intention certainly is to publish and share that. And Keith, I think as you point out, there are a lot of potential ways to, I hope, leverage this to inform different risk and resilience measures at the community scale. But our first one will be the measure that Catalina kind of pointed out at the beginning, the loss of access to critical facilities and socially vulnerable populations. That's what we have some kind of active work trying to understand, how debris influences transportation infrastructure and access within a community.
So there are a couple questions coming in the chat. Ali asks, did you consider the uncertainty related to different hurricane intensity? Is it in terms of debris?
Okay, so that's a good point, and that's something that we have not strictly considered right now. So what we have as in terms of the storm intensity parameters, we're taking the peak value of the time history to inform that particular location. So after the simulation of the storm using a software such as AdCirc or +1, what you will get is the time history in each one of the grid points of the computational domain that they use to model the storm. So what we do is actually taking the peak value of each one of those parameters. So right now we're not incorporating uncertainty, but in future work we will try to do that based on some distribution of the uncertainty parameters.
All right, thanks, Catalina. Do you have anything to add, Jamie?
No, I was just going to suggest to Alex Akato to maybe reach out to me separately by email, and happy to connect. Thanks for your interest. And then I think Ryan had a question. Was the area of the building the only factor used to determine the fragility? Can you take into account other parameters like age and building codes? Catalina, do you want to point out Tomacek's model and what we consider based on her work?
Yeah, so for that one, and actually right now we're considering also based on another data set, the number of stories, because right now at that moment we only had like the footprint of the building. Right now we brought together some data coming from the tax appraisal data of the Houston Galveston region, where we also will have, for example, the number of stories that will also influence kind of that potential to generate debris from that site, from the construction site. Related with the aging, that's very interesting, but that comes what Dr. Pajo was mentioning, that it was the fragility function that was used. So this function is an empirical derived fragility function, and it does take into account kind of the age of the building in terms that it has different age groups. So I think I'm going to share that in the next slide before the hands-on exercise. But there is a parameter that informs the fragility function apart from the ones related with the storm that is related with the construction year. But definitely this is a fragility function that we're leveraging for this study, also because it's in the aftermath of Hurricane Ike. So it's very related to the data set that we're using. But in future studies, these parameters can be informed by different fragility functions where you could start implementing other things related with the vulnerability of the built environment, or even things related with the kind of distribution of the intensity parameters.
And maybe one thing to add, so Ryan, I definitely want to acknowledge Tori Tomacek. So the fragilities that we're leveraging were not fragilities that we derived in our group. It's part of Professor Tomacek's work with collaborators. Our framework, I think, is amenable to incorporating different fragility models, but I think the early idea is just to test the kind of relative importance of capturing physical structural damage relative to other things like vegetation and density and things like that. And the other thing that I think we acknowledge is that even in our current best state of structural fragility modeling, which is a field that I love and I think we could do a lot, we still are not able to capture a lot of features. For example, there are ancillary structures, sheds, or there are just possessions that people have that become debris, and then there's the vegetative debris. And so we don't actually have adequate physical fragility models to predict damage of all of these. And so that's why we're trying to test other proxies and understand their relative importance with the density and presence of those other features.
Mm-hmm. Yeah, that's more of the part that I'm doing right now, that is actually testing these other things related with the accessory structures like barns and other things that might be present in a parcel and its potential. So very excited about the next phase of the project that it will be out soon. There's maybe another question, and I don't know if last, but it's related with the data is integers. Okay, so you're asking if it is, the question is if I'm using, for example, other types of data that is not numeric. It could be like classifications of some other things. So no, all the data that I'm using as predictors are numerical values. Also because when we were testing, these models, for example, the Gaussian process, is better if you have these numerical descriptions, because the model then can be able to capture these different parameters. And let's see kind of what is the variation of the parameter in its space, and kind of capture if these parameters are going to be important in the debris prediction model. So I'm using like integers, like numerical values. Climate change can have multiple impacts. Okay, another question. Sorry, there are a lot of questions, but there's one that says, by Ali, climate change can have multiple impacts, hurricane intensity, that's true, and effects on vulnerable human groups. Which kind of impacts is focused on your work? So I'm kind of, in my PhD work, I'm analyzing kind of both. But in this part of the debris model, we're analyzing more the impacts of, maybe you're thinking more about the ongoing work related with population projections. So related with population projections and how we're using it to couple with climate change, the IPCC has some scenarios for example, climate change that are based on the concentration of emissions in the atmosphere. Those are called RCP scenarios, representative concentration pathways, in the sense of how these, for example, measures that we're going to take related to climate adaptation are going to influence the socio-demographic features of in the future, for example, in a community of a region. There is another set of predictors that is called SSP, social shared pathway. I forgot the exact definition, but they're called SSP scenarios. So they're kind of coupled. So the climate change part is also, it kind of takes into account that part of how the population projections are going to change. And our end goal, as Dr. Payet mentioned, of the cascading consequences are going also to see how these impacts in the population projection, in the concentration scenarios are going to influence, for example, have cascading consequences on socially vulnerable populations. So I hope that answered that part. And can we adapt the current approach? Yes. Can we adapt the current approach for the re-estimation at other levels? So that's something I'm also doing right now. I'm doing we're doing a sensitivity study, not only with the first kind of grid cell, that it was the 500-meter one, that is a big area. We're also using a smaller grid cell size right now, that is 30 meters. So it can be adapted because it also always depends on the resolution of the data that you will have and how small can you go, depending on what is the small feature that you're going to fit into the model. So yes, you can go at different resolutions, and that's something we're working on right now, actually. Thank you, Dr. Ans, for your comments. Okay, I think this is another question. I have a question. So the uncertainty of the data is all taken care of by the machine learning. Are they okay? So there is a different thing between uncertainty, what a machine learning model will do, and what a probabilistic model will do. And actually, that's what I'm trying to bring with a Gaussian process in this second part of the project. So a machine learning model, well, it's a statistical model. It will give you kind of what you will think is a mean estimate of the prediction that you're seeing, but it won't give you kind of well, there are certain models, for example, such as Gaussian process, that is kind of a random field model, to be exact. So it will give you kind of a probabilistic estimate of what you will have in the debris. But right now, these other machine learning algorithms that bring into account, for example, random forest and other things, there are statistical models that are very powerful, but it will give you kind of a value. So you can think about it as a mean value, but it won't give you any probabilistic estimate. In this second part of the talk, of the work, we are using Gaussian process precisely because of that, to get a probabilistic estimate and get different like values of debris volume over that region. And I don't know, I think
there's one question from Hiba with your hand up. Do you want to unmute and ask?
Yeah.
Thanks for being brave and asking.
Hi, Catalina, this is Hiba. So I didn't want to put my question on the chat, but started just to talk here. So I'm gonna ask you a question regarding to the part where you were talking about the performance of the different models that you established. you showed 3 models, 2 of them using the debris presence data, debris presence information, and the third one without. And you showed that the first 2 perform better than the third one. But I was just curious because based on the table that you showed, the error with the debris model using the classification model is better, is like less than the one with the actual data.
It's like, yeah. The thing
So
is that
how you can explain that?
it's less, but the difference, you can understand that as a numerical, because if you remember the table, it's just the second decimal point. And it's actually, I just put 2 decimals, but the actual difference is in the third decimal point. So when you come to the third decimal point, you can understand that that might be just numeric things of the model. So technically, that's why I said there is not much difference. It's just because of that. But technically, if it would be, or if we're using another, that's another big field in this area of how do we actually evaluate the performance of these models. That is not just related, for example, of adjust I-squared. That is something we tend to use because these models are not linear. So actually that won't tell you something. So there are different measures. I'm also trying to incorporate now that into these studies of how can we use different measures to actually say the performance. So thank you for your question, but it's more related because the difference was the third decimal point. So it was numerical thing.
I see, but it's very cool that like both models are performing almost the same. So great work.
Yeah, yeah, that's exciting. I agree.
All right. Well, thanks, Jamie and Catalina, for the presentation. And I think that it's probably time to move on to the hands-on portion. So Catalina, do you want to describe kind of how that's going to work, and we can do that?
Yeah, great. So I'm going to walk you a little bit of why are we going to do this hands-on exercise, and what kind of is the reason behind we in our group developing some of these scripts to help us in this part of risk analysis and developing machine learning models. So I'm going to share my slides a little quick here to show you a little bit of the background. But you can start by opening, by logging into your DesignSafe account and opening, and I'm going to walk you through. I'm also going to share actually right now in the chat. It's not the final documentation of this case study, but I made a guide for you guys. So in case you cannot see it right now, or if you encounter one problem in DesignSafe or something, you can always use that guide to walk you through the main steps of what we're going to do for today, okay? As I said, it's not the final documentation of the case study. I think that's coming later on the year, but it will give you an idea. So first I'm going to share that file. So then I can go to the slides and we can start the, how do I share files? Let me see. I have never done that.
You want to actually like upload a file for people to download?
Like a PDF, yeah.
PDF. I'm not sure that this Zoom will allow us to do that. I don't see that option here.
Okay, well then it's okay. I mean, you can see it on my screen. It's fine. So let me share my screen again.
Do they need it right now? Because we could always email it to the registrants later.
Yeah, yeah, that's okay. Maybe we can just email it. I'm sorry. It was just for everyone to have it as a guide if they wanted to play with the codes later on.
Okay.
Okay, so let me share my screen. So, okay, so we were here. I think I actually didn't acknowledge, but this is our funding sources, the National Science Foundation, DesignSafe Infrastructure, and Rice University. So we're going to move to the second part that is related with the hands-on exercise. So as we were mentioning, some of the work we're doing right now is expanding the set of predictors that we're fitting into the machine learning model to do the debris volume prediction. So we're going to go into more detail in how you would compute, for example, one of the ones related with the probability of failure of the built environment. So as I was mentioning, and this is related to one question we got in the chat, the probability of the fragility function that we're using, proposed by Dr. Tomaszek, actually takes as input parameters the significant wave height, the freeboard height, that is actually kind of, you can understand it as what is kind of the space between the water and your actual house when the house is elevated. And for this parameter, actually, you will also need what is the surge depth. So that's where we're going to extract these two intensity parameters are out of some abstract simulations. And here we can also see that question, like there is age. So age is understood as different classifications of it kind of comes from 1 to 4 different age groups, and it depends on when your structure was constructed. For example, the structures that are in the age group 4 are the ones that were constructed after 2000, like counting 2000 as well. So a little bit about this part is we will need the intensity parameters related with the significant wave height and the surge depth to find out this predictor, because it will inform the fragility function and will allow us to compute the probability of failure. So what will we ultimately need is we will have kind of point estimates. That is the output of the abstract simulation. And we will also have a portfolio of structures in our region. For example, this is some structures in Galveston Island. And what we actually want to do is couple the storm data, let's say the hazard analysis part, with each one of those. So how do we extract what is the specific surge depth and wave height at each one of the houses? So that's what we're going to do today. So what we propose is an automated processing of these storms, because probably when you're developing these models, you won't do it just for one particular storm, or you will have different intensity parameters, like different levels of that intensity parameters. So we start with the building portfolio. In this case study, we're going to use the building portfolio of Galveston Island. We're going to load the wave height and surge data that comes from AdCirc after some pre-processing. We're going to go to that script, that Python script that will allow us to do that. We load that point-based surge elevation and wave height. We're going to create a surface, a raster of each one of these intensity parameters to actually extract the value at that specific house. And we're going to export this as a CSV file. That is something that we use for the other post-processing or creating the model, for example, in Jupyter or in MATLAB, creating the machine learning model. And we will do this for each one of these terms that we want to analyze. So what we will have at the end is for each building location, we will have the intensity parameters related with the surge depth and wave height at each one of those points. And we're going to leverage the DesignSafe infrastructure, cyber infrastructure to do so. So just to be a little bit more explicit about what we're going to see today, we're going to see a script, a Jupyter notebook that will allow us to read outputs from AdCirc and give us to us in a format that we can bring into QGIS or any GIS software that you're using. So we're going to extract it as a CSV file. We're also going to use Python scripts to automate this process of geospatial analysis. So that part of how do we extract from a surface of surge depth or wave height the value of each one of the parameters, and how we do this in an automated way, not doing it by hand every time we need a new storm. We're going to see at the end how QGIS enables us to couple these different data that has different spatial resolution. So first, we're going to go to the data depot to do the data management, gather all the files that we will need for this case study. Then, as I mentioned, we're going to read the AdCirc outputs and extract the intensity parameters in a particular region. And then we're going to go to QGIS and use the script that will allow us to extract the different intensity parameters at the particular locations of the building stock. And then we're going to do some visualization of the outputs. And if time allows, we're going to export them as a web map. So let's start. I'm going to now share my whole screen, now that we have a little bit of background, to show you how we will start. Let me share screen. Yeah. So can you guys see my DesignSafe account?
Yep, we see it.
Okay, great. So the first thing, as I told you, please, if you haven't done so, please log into your account in DesignSafe. I'm already here. And welcome, Catalina. Please, if someone is getting behind for too long, you can either see my screen or you can let me know in the chat, just in case I can slow down a little bit. So the first thing we're going to do is create the data management part. So we will go to workspace and then we will go to data deep. You will be in my data folder. If you're not there, click my data folder, and then we will click add, where we're going to create a new folder, and this is going to be your working folder. This is where we're going to get all the different scripts and all the different information, and the one that we're going to access through QGIS. So give your folder a name. I will call it, I don't know, 0 DesignSafe webinar. So it appears on top. And then we will give it to create folder. So here, now in my data, you should have your folder that it should be empty because we haven't added anything. Now, there itself in the data depot, we're going to go to community data, that it's right here above help. So we go to community data, and then we're going to search a folder that is called use case products. Use case products. Here it is. It's called use case products. We click there, and you will have 3 different folders. We're going to use this one that is QGIS. Don't click. Click the little box that is next to QGIS. And then here on the top, kind of on the right, you will see one that says copy. Click copy. Here it should be my data. It should be my data. So you will be able to see all the different folders that you have in your my data folder. And click copy to the one that you just created for this hands-on exercise. So mine was called 0 DS webinar. We're going to click copy. It says copy operation has started. Copy operation was successful. So now, before going to our folder in my data, I just want to show you a little bit about what you will find in that QGIS folder, because it takes a little while to kind of copy some of the file. Sorry. So here in the QGIS, we will have 2 different folders. One that is called read at circ, that is the one, as its name says, is going to be the one related to reading the outputs of at circ and us getting it into a CSV format. So if you click here, you will have, as an example, I provided these files of one of the storms we're going to analyze. So you will have this 463 NC file. That is the output of AdCirc that will give you the information about the search elevation at each one of the grid points of the computational domain of the simulation. And you will find this file that is called swanhs.63 that has the information related with the significant wave height. And there are going to be 2 different Jupyter notebooks that, as its name say, are going to read the search one. I call it search Galveston because our case study is going to be in Galveston Island, and the other one that is related with the wave height. Then you come back to the QGIS folder, and we will find the other folder that is called IM extract, so intensity measure extraction, where we will have 3 things. So we will have the complete building data that is actually going to give you, as an example, in this one, for example, what I do when I'm going to do my analysis is I don't only give it the location of each one of the houses, but I give it more information regarding, for example, the year it was constructed, I don't know, the type of foundation, and some other things that I need to evaluate other parameters. So just here for this example, I'm just giving you the geographical coordinates of each one of the houses. You have the Python script that is going to allow us to go to QGIS and do the whole automated process. And then we have a storms folder where just for this case study, I just gave you some outputs for 3 storms. So actually these are some storm simulations of storm FEMA 33 that is also a probabilistic storm that will give you still water elevations kind of approximate to a 100-year return period storm in the Houston Galveston region that have different forward velocity and sea level rise. So in each one of the folders, you can go to all of them. All of them have the same information, but you will find 2 CSV files, one with the search data. Actually, the peak storage, as I mentioned in one of the questions, is the peak storage and the peak wave height at each one of those locations. And in the other storms, you will find the same. You will find the same two files. So now we can go to my data.
Hey, Catalina, real quick, you're doing a great job. I just wanted to offer to put the PDF in community data. If you wanted to send it to me or to Charlie, we can put it in community data where people could access it if you want.
Yeah, great. Yeah,
you would have to email it to us or get it to us some other way though.
Okay. Yeah, that's fine. I can send it to you over right now. Oh, we can do that right now. Yeah, I guess.
You could do it right now if you think people need it now, or you could do it afterward and then people can find it later.
Well, maybe just in case you guys want to, but yeah, I think we can do it both ways. So I'm going to just stop sharing for a moment while I enter to my email. Just give me.
Yeah, we don't need to all see your email, so that's fine.
I can't find your email. Could you please give to me? Or Charlie's? I just can't find it right now in my email. I don't know what.
I'll put it in the chat.
Thank you. Thanks. Okay, send, I think.
Right. I'll put it there. I'll just put it, should I put it in the use case folder or like in the QGIS or?
Yeah, I think that's
right
fine in that folder.
Okay, I'll do it.
Thank you. So in case you guys want to follow what I'm doing, some of the main steps are there, or if you want to do it by your own later, that's also fine. But we have a new documentation of this complete case study coming. So this is just meanwhile. So now let me share again my screen. Where is it? I don't find it. I don't. Okay, great. So we were here. So now we're going to go to your My Data folder, search for the a folder that you were working on. In this case, it was 0DS webinar. It should be there, the QGIS folder that we just copied. Let's go first to this one. You should have all the files that I just showed. So yes, you have the 3 storms. You should have that as well. And then let's go to read that CIRC and let's see. This is the one that takes a little bit of time to copy. So since these files are kind of heavy, the ones related with the outputs of CIRC, it just takes a little while to copy, but it's there. So you should be able to see this, or if your computer is faster than mine, you should also see the one. There is one question. Oh, okay, sorry. So for example, let's start with the one related with storage. So we're going to click there. Takes a little moment to load. We will see it there. And then here you will see that says open in Jupyter. So click there. So I hope everyone is there, but you will be able to open. Maybe sometimes it asks you to log in again. So you will just have to log in again. But hopefully you will see a Jupyter notebook like this. I have to mention first, I'm not going to do this because I already installed it, but in this cell, if you haven't installed this package, you can just delete this part of or. Sorry about that, I left it there because maybe we will ask you, maybe this won't run because you won't have this package. So first, kind of uncomment this part that says pip install net cdf4. And actually, sometimes I have found that people those also have the package Shapely. So you can just copy the same thing, pip install Shapely, just in case so it runs smoothly and you won't have any problems with it. So I will just give us 2 seconds, but I hope everyone is there. Let's go back to here to see if the other file has loaded already. It's still taking some time to load. Yeah, it's starting to copy. No, it's already copied the whole thing, so that's good. How do I move this? That here. So we can actually now that this is also copy, the one related with the wave height. Let's also click wave, gulf. And I suppose we don't have to wait. Let's just click open in Jupyter. Okay, so it's the same. In case you don't have installed these 2 packages, netcdf4 or Shapely, do the same. Kind of uncomment this one. I'm not going to do it. Delete this part of or. I'm going to do it right now. And just copy paste and change the last part of netcdf4 for Shapely, just in case you don't have those packages. More likely that will happen. I have them, so I'm just going to comment it again. So let's just run for cells, just in case someone will have a problem with this first part. So you will just hit run, 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 run. Here is going to read in this cell the actual file. Here in this part of the code, since these files are so big, like whatever output you will get from Attrick is big. And usually when you're doing these risk analysis studies, you just need for a particular region. What I did is just extracting the outputs, so the intensity parameters at a particular location. In this case, I got Galveston Island. How did I get these particular coordinates? It's very easy. You just go to Google Maps and you just get the part of the area that you want to see. You right click and then it should appear kind of the coordinates. And you just put them by pairs. So that's how can you create the kind of the polygon that you need to extract for the area you want. In this case, we're not going to change that because we're going to do it in Galveston Island. So we're just going to leave it unchanged. This is just kind of for me to know how many nodes are there. So you can see there are a lot of nodes. That's why we're extracting in a particular region. And this is actually the cell where we're going to create the CSV file. As you can see, for example, here in the IM extract, I'm already giving you the CSVs because it takes time to run. Since it's so big, it just takes time to run. So we didn't have time to wait for those results to be like copied. So I just gave you the results, and but like we will just run it. Once you run this, well, we will run it. I think we were here. Sorry, I was here. Guys, let's just run it again. Run the polygon. It loaded the node data. And now run again, it should appear star. I see here that there is like a little clock. That means it's running. So you just leave it there. It will take maybe, sometimes it takes 20 minutes, sometimes it takes half an hour. So you just leave it running. What will you have at the end? And you do the same with this file. We can do it. I'm not going to do it, but you do the same. You just run the whole cells. It's the same kind of code. And what you will have at the end, I think I have a test, but what you will have at the end is that in this file, and please, if you find a problem with that, just send me an email. But what will happen is that in this read at circ, and I think it should appear, you see, it appears, it starts appearing as search max CSV file. So don't open it, it still says 0 byte, but it's creating it. So it will, when it completes, the whole CSV file should be there with the intensity parameter that you're analyzing. I call it search max here, and that's something that I tell you in the guide. In the guide, there are things related to it, where do you change each one of the parameters of the Jupyter notebook. So right now here, I'm calling it search max, a CSV file as an output. So that's what you basically do with this. So at the end, you will obtain a CSV file. We're going to open the ones that are in the other folder, but that's how you will create the CSV files from at circ outputs. I'm just going to close this one and leave this one there running. Hopefully by the end of the session, we will be able to see something. So let's go back now to Data Depot, to this one. Let's open just one for you to see what you will have at the end when the script is, for example, search max. It takes a little moment to load. Yeah, so what you will have is for each one of the points that you were extracting on that area. So you will have the longitude, the latitude, you will have the peak search elevation at that particular location at the time step that it happens. Since I told you at the beginning, this is like a time history. So it also tells you what is the time instant where this peak search happens at that particular location. And that is what you will obtain at the end once this Jupyter notebook runs. So now this is the actual thing we're going to work on. So now let's go to work. Let's click workspace. Before you click tools and applications, just hit control tools and applications. So it opens a new one, and it doesn't change this because I want to show you how some files that get created in this folder. So you will go to tools and applications. We will go to visualization, and here you should find QGIS desktop. You will click there. This is more related to the desktop resolution. Depending on where you're doing it, you can change it. I'm just going to leave the same one, and then give your job that is going to open a new window with your QGIS extension. So just give it a name. I'm going to call it the same way I called the other one, 0DS webinar. So it appears on top. Once you change the job name to whatever you need, you will click launch. You can click refresh. It says submitting. Soon it will change to running. And then soon enough, it will open a new window with
This is probably a good test of the QGIS cloud interface with like 20 people doing it all at the same time, right?
That's true. Sorry, I didn't show you. I just hit connect, but it just appears a window. So click connect, and yes, it's starting. Yay. So okay, so everyone, all of us, I hope all of us are here. So it opens a new window. We're just going to create a new project. So you can just hit Control N, or here, like right beneath project, you will find like this page. You will click there. It opens a new project for you. Okay. Then what we will do is we see in this toolbar, kind of at the end, you will see kind of this Python icon. Hit there to open the Python console. Take some moment. It will open kind of this console here. You see here there is kind of the third one that says show editor. Click there as well. I'm going to close it because this was the one of the test. So here we will open the new kind of the script that is in our folder. So here, click this icon of folder, open a script, and then you will go to Ubuntu. You should have one folder that is called My Data. Just double click there, and then let's go to the folder that we just created for this case study. So we will hit DS webinar, QGIS, IM extract, that is where we have our Python script. And here you will have the Python script that is called IM extract. Then click open. Okay. So hopefully we're all there. Let me see if I can move this. It's not moving. Sometimes it moves. Okay, now it's moving. So now, the only thing that this is kind of in the guide, and it will come in the guide, I think in May. But the first thing we need to change in the script, and actually it tells you here at the beginning, please change the folder path in line 17. So we will go to line 17. And we need to change the path. So what we're going to do is here in the icon, like in the bottom of the screen, I hit this open, you have this, the second one that says File Manager. Open there. You find kind of the same thing when we were opening the script. Then you will go to My Data. And you will go to this one, QGIS, IM extract. And you copy that file location. Control C. Then you come all the way, everything that is between the, oh my God, I forgot. Everything that is in between. So here, including kind of the slash, the backslash. So then you click Control V. So it will change it. It should look something like this. Home Ubuntu, kind of the My Data, the name of your folder, and then the name of the QGIS is going to maintain the same. And then maybe why is this so small? Let me see. Okay, this is the reason. Yeah. And then you will have QGIS that all of us should have it the same, and this IM extract as well. Okay. There are other things that you can change in the script, and it will be seen here. For example, you can change the cell size. We're not going to change it because in this cell size it runs quickly, but you can change the cell size of the raster that you're going to create. It tells you the line that you should modify it. And you can also change the interpolation method to create the surface. So you can play with those things later, but for today, we're going to leave it the same. So that's all we need to change for this script right now. So once you change the path, let's just click run. And I hope it runs. Yes. So it hasn't appeared any mistake. Here, it should appear the time it takes to run the script. And here it will appear all the layers that, it took when like running the storms. So it usually takes like 30 seconds, a minute. So let's just wait. This is still running. So yeah, it worked. So now we just make this small. So here it will tell you how much time it took to run the code. And here on the left, on the bottom left, we will find all the different layers that were created when analyzing the storm. So remember that we have 3 storms in the folder. We have this one, and this one. So for each one of the storms, it will create one survey. It will load the data for the wave height and the surge max. And in this case study, I just extracted it at this particular storm. So for this one, you should see more layers. One of them is going to be called surge max building and wave edge max building. That means that you will have at those particular locations the building and each one of the storm intensity parameters. So for example, let's open this one. You will click, you just right click on the layer. Actually, we can do it with another because I just load that particular layer, but it happens with all of them. Let's click this one, right click, then you will say open attribute table. And you will find each one of the location of the houses, the coordinates, and you will have the value of the search, oh my God, wave height and the search elevation at that particular location. And you will have that for all the building stock, okay? So that's what you will have. So right now, to visualize better the outputs, I'm just going to not see all the layers, because then all the layers are going to be there and we won't be able to see. And I'm just going to I'm just going to keep one layer on that. I'm just going to do the one of search max building. Then click there, then right click and go to zoom to layer that I don't see it. Oh, zoom to layer. So you will have, for example, in this case, Galveston Island, and these are all the building locations, and you will have there its particular values. So what you can do to visualize the outputs, you can play with it. So you're going to right click again and you go to properties. Then you will go to symbology. And here you can change the color of the one. So I will just put a very nice purple color. Then, for example, I'm just going to reduce the size just because the size of the points is too big. So it doesn't let me see a lot of things. So I'm just going to put like 0.8, that's fine. You can play with all these things later. For the sake of time, we're not going to do it. You can also add a legend and different things. I think there's also something with opacity. I'm just going to give it a little bit. 90 should be okay. And then you will just click OK. There. So we will have the layer. Just to be able to, oh, I just got it floating. It's okay. We're just going to close that. And one very cool thing about QGIS, this allows you to export these layers to a web map. So what is a web map? It will allow you to see whatever you have here in QGIS, but in your browser. So it will open in your Google Chrome or whatever. And that's something that you can share with your collaborators. So for example, if you're giving a talk, you're giving, I don't know, in a conference, you have different layers and you want to play with each one of the layers, even search particular locations and zoom there, you can use these web maps to do so. So what we're going to do is go to plugins, manage and install plugins, click there. And here we're going to type QGIS to web. I did it wrong. I already installed it, so I'm not going to uninstall, but in your screens, it should appear something at install. So you just click install and close. I'm going to give it a couple of seconds. I don't know, if someone is doing it, please feel free to tell me that it installed. But you should be able to install it.
Yeah, mine just finished.
Okay, great, thank you.
I pushed the button right before you told me to, so I'm glad I did the right thing.
Great. So if everyone is there, thank you for letting me know. You should go to web. It should appear here also between mesh and database. You will hit web, then go to QGIS to web and click create web map. Right now, we just have one layer on, and that's what we're going to do, so it doesn't take a lot of time. So you will have the search max building, that is the layer that we want to export for today, but you have different options there to change and to appear in the part. In appearance, you can always search things. For example, today we're going to click on add address search. So this will allow you in the browser to type an address and it will take you there. So that's a cool feature. We can also add measure. I think measure tool is here. You can also, let's say, metric system. That's okay. We're going to leave it there. This is very important. Now you will go to the export tab. And here, right beside export to folder, click those 3 dots. And again, go to the folder that you're working on. So you will go to my data, DS webinar, QGIS, and IM extract. It can be like also QGIS, but I want to put there. So sorry, I think I made, yeah, just click the folder where you want to like put it. If you made a mistake, just click this arrow, it will take you to the previous one. And you will just hit choose. And then you will just hit export. It's telling you that it's exporting. This is, it doesn't matter, it's something related with the audio. and you just click OK. Then we just wait a couple of seconds, and you see by its own, it opens Explorer window, and it takes some time to load. That's true, but we will start seeing the folder that the file that we just had, and you can zoom in, you can zoom out, you can do like the widget that we just installed, for example, that was just to search addresses. You can search whatever address you want. Right now, I don't have one handy, but if you have an address, you can just click there and you can do it. You have the measure tool. Then you, for example, you will just click 1 point and then go to the other point, and it will tell you the distance. So there are a lot of things that you can play with that I didn't show you, but just for the sake of time. So the other cool thing that I mentioned at the beginning is that you can share this with people. So if you go back to your data depot, let's just refresh, let's say, the folder that you were working. This was my working folder. You go to IM extract. You will see that there is a new folder that is called QGIS to web and then something else. So then you're just going to click there in the little box and say download. I'm just going to do it here, save. You will just go and open it in your folder. I don't know, it's not opening. I will just go by this. It's going to be a zip folder, so you just unzip that, extract files. Okay. Are you able to see my Explorer, or is just the DesignSafe still? I don't know, because I'm not sharing a screen.
We're seeing just your DesignSafe browser.
Okay, then maybe let me stop sharing. I'm going to share my whole screen. That's easier. So you should be able to see my Explorer right now. So what I did is just download it. It just downloaded as this name, download to. I extract the files, and then you will see this. If you see this in your own computer, you just double click the one that says index, and then in your own browser of your local computer, you should be able to see the map. Again, it takes some time, but it will open. Well, maybe we can come back to that at the end, but it will open. So, oh, here it's starting to appear. It just takes a little while. It's very heavy stuff, but once it loads, it will look something like this, the same. So that's the end of my presentation and the hands-on exercise. Just wanted to let you know that you can implement this same kind of procedure to extract to different kind of levels. Here we did it for a building stock, but we can also do it for block groups or even for transportation networks. You can also use QGIS to just visualize outputs to kind of have an idea of what is the hazard over the region that you are analyzing. This is something I did with the storm example I uploaded. Here we have a map of the surge depth and the significant wave height in Galveston Island. And yeah, well, thank you. I hope you learned a lot today, and I'm pretty glad I did it on time.
Yeah, great job, Catalina. I'm also glad that QGIS worked. Live demos are always a risk, so it all went well. So thank you very much for being here.
Oh, you're welcome.
Yes, Catalina, thank you so much. And congratulations and good luck with your studies. That was an amazing presentation, and that was a really great live demo. As Scott said, live demos are difficult. So thank you so much for thank you so much for your time today. Really appreciate it. Hey, everyone, when this video gets curated and published, it'll be published to our DesignSafe archive. If you go to DesignSafe Learning Center training, the DesignSafe archive is linked off of there. You'll see all of our past Design Safe webinars there as well. And as soon as this one's ready, it'll be posted there too. If you have any questions in the meantime, feel free to contact us and we'll make sure that Catalina and Jamie get your input. Once again, we really appreciate your feedback. So if you didn't get a chance earlier, here's that QR code again. So if you scan that and go ahead and give us your feedback on this webinar and on any future webinars you'd like to see, that'd be very appreciative. Thank you. And once again, thank you, Jamie, and thank you, Catalina. That was an incredible job. Great presentation. We really appreciate it. If you have any questions or anything, contact us on Slack or email us at training@DesignSafe or fill out a ticket on DesignSafe. And once again, everybody, thank you for your time and thank you for your participation. We really appreciate it. And we'll see you all next time. Thank you.
Bye.